So if we take a look at our formula sheet under vectors, we can see all this cool stuff here. Now these bottom two, we've never spoken about them before, and that's what this video is about. We're looking at the vector equation of a plane, and we might touch on the Cartesian equation of a plane, but this is the top one. We're most interested in that one at the moment. So what is a plane? Let me show you a plane. This is a plane. So we're in 3D here, and a plane is just a flat surface. You could walk up this hill. Now this plane could look like a little bit more like this, right? We could sort of move it around a little bit. We can rotate it around a little bit. We could make it flatter. We could rotate it this way a little bit. These are all examples of planes. If you don't want to deal with that, instead just pick up a blank sheet of paper and make it very, very flat. This is a plane, this is a plane, this is a plane, this is a plane. Planes are infinite though. So imagine this piece of paper was infinitely large and you could manipulate it like this. That's what a plane is, and that's what we're going to be doing the equations of. Now a formula that's going to be super useful is this one here. R dot n equals A dot n. It's the vector equation of a plane. Let's write it down. Alright, there it is. R dot product n equals A dot product n. Now probably important to note that these are all vectors. So it's vector dot product vector equals vector dot product vector. But what are these vectors? How are we supposed to find them? Let me draw a plane. So there is my very crude drawing of a plane. It's a good place to start. Now I'm just going to draw like an origin. So this is the origin here. We'll call it O. And that is point 0, 0, 0. Alright, if I put a point on this plane, I know a point, right? I know this point here. We'll just call that point A. Alright, the vector that connects O to point A is vector A. Alright, so vector A is just the position vector of a point on the plane. So to be very, very clear, if point A was 2, 1, 0, then vector A would be 2, 1, 0. Okay, that's good. We've got this vector. It's the position vector of a point on the plane that we know. We know that point, or at least we can figure it out somehow. Okay, what about n? There's n. N is a vector that is normal to the plane. So if I had my plane here, let's go in 3 dimensions, right? And we've got a flat plane. This vector, if it makes a right angle with the plane, we call this the vector that is normal to the plane, vector n. You can see I've drawn it with a little right angle here. Now, importantly, in our formula, you can see n appears twice, vector normal to the plane, vector normal to the plane. We're substituting whatever that vector is straight into there, which just leaves us with R. And R is probably the hardest to wrap your head around. R is every single vector, an infinite number of vectors that hit the plane from the origin. Right? This is R here, but so would R be here, so would R be here, R be here, R do a bajillion infinity vectors from the origin hitting the plane. So R is going to be a variable vector, right? Because it's all of these vectors. It represents every single vector that goes from the origin to the plane. Now, with all of this information, we could now do a question. So, if we know a point on the plane, and here's our picture, I know a point on the plane, 2, 1, 0, and if I also knew the vector normal to the plane, let's put in one for this one. Okay, normal vector, 3, 2, 1. So if I know a point on the plane and the normal vector, I can plug all of that information into my vector equation of the plane, and I'll know what the equation of my plane is. So this is how the question might be phrased. Determine the vector equation of the plane containing point 2, 1, 0 with a normal vector of 3, 2, 1. And we're very simply going to write our formula. R dot n equals A dot n. And then R is just R. It's any and all vectors, right? So it's just going to be R here, dot. The normal vector is 3, 2, 1. A is the point, 2, 1, 0. And N is our normal vector, 3, 2, 1. All right, we're basically done. Really, the last step here the left-hand side really stays the same. We can't really do much with it because r is just our vector. We're kind of stuck with it. So r dot 321 equals, and then we do the dot product of this. 2 times 3 plus 1 times 2 plus 0 times 1. I hope that's 8. I'm finished. That's it. This is the vector equation of a plane. If you show this to someone, they should then be able to create that plane for you somehow. All right, so this is all very, very cool, but you're probably seeing the second formula and wondering, okay, that's the vector equation of the plane. What about the Cartesian equation of the plane? All right, so we're going to be asked to do the same thing, but this time we're expressing the equation of the plane above in Cartesian form. So we're going to take this and write it in Cartesian form. Now, the trick here is to understand that r is any and all vectors, right? So what I'm going to do is replace r in this equation with a vector that is just x, y, z. Okay, so this is r. r is x, y, z. So now I'm going to do x, y, z dot product 321 equals 8. Okay, and you might be looking at it going, yeah, but what did that fix? Well, now I can kind of do the dot product. I can say 3x plus 2y plus 1z, or just z, equals 8. Now, this is a perfectly good equation of a plane. You can see it's being expressed here as 3x plus 2y plus z minus 8 equals 0. But everyone would accept this. This is an excellent answer. We're going to stay here. 3x plus 2y plus z equals 8. There we are. We've expressed the equation of the plane in Cartesian form. Super fantastic. Now I'm going to get rid of most of this, but I do want to stay with this equation of the plane just for a second. All right, so those are the two questions we've done so far, so good. Let's add another question that's related to these. So here's the question I'm being asked. Is the point 423 on this plane? So you can use this information, you can use this information. It doesn't really matter. Both of these are going to let you do it. Remember what I said. R is the position vector of all of the points on the plane. So if 423 was on the plane, I should be able to put it in here. So I should be able to say 423 dot product 321 will be equal to 8. Now, if that's true, then yes, that point lays on the plane. Does it? 4 times 3 is 12, 4 is 16, 3 is 19. 19 equals 8. So, does this lay on the plane? No, of course it doesn't, because 19 does not equal 8. Now, of course, we could have done the same thing here by putting 4, 2, and 3 in there. And what would we have found? We would have got 19 equals 8, so the point doesn't lay on the plane. So let's not end with that anticlimax. We've got this one here. Is the point 2, negative 2, 6 on the plane? We can do the same trick. We're just subbing in 2, negative 2, 6, 2, negative 2, 6 into our equation. 3, 2, 1 equals 8, and seeing if it works. 6, negative 4, let's do it. 6, negative 4, 6 equals 8. 6 plus 6 is 12, minus 4 is 8, 8 is 8. Yes, it does lay on the plane. Now, there are some more things I want to talk about when it comes to equations of planes, but this video is long enough. I'll catch you in the next one. You don't know everything yet.